This is Lab 5 of the AMD Xilinx FPGA Vivado flow, and in this video we will be discussing Xilinx design constraints in the context of FPGA design. Specifically, we will be walking through a lab exercise focused on setting up an I/O input-output planning project and analyzing timing constraints. After completing this lab, you will be able to achieve several key objectives, such as you will learn how to create a Vivado input-output planning project, and you will end up in locations and input-output standards using the device view, the package pins tab, and TCL commands. And finally, you will perform post-synthesis and post-implementation timing analysis. So the practical application for this lab is a UART receiver design, where the system receives input typed on a keyboard and displays the binary equivalent of that character on the onboard LEDs. When a push button is pressed, the lower and upper nibbles of the binary display are swept, that we will see in the coming demonstration. And this lab supports two target development boards, the PINZ2 and the Boolean board. But in this demonstration, we will be using the PINZ2 board. So the first step in our workflow is to create a Vivado input-output planning project. So we start by launching Vivado and utilizing the create new project wizard, and then during the setup we specifically select the IO planning project option, and we then filter and select the appropriate hardware part. Like for the ping Z2 we have to select XC7Z. Like this board, yeah, it is given here. So we have to select this board from the filter part, and next we define our inputs and outputs. So first of all, you have to create this project and click on the finish button. Then you will get a screen like this, and then you have to define our inputs and outputs. So for that you have to go to the flow navigator that I can show you here. Actually, I have already completed the first initial steps, and this is the thing that I am getting. So yes, let's remove this. So first of all, you have to define inputs and outputs, and then we create input ports for clock pin, button pin, and reset pin. And then using the device view and package pins tab, we assign these to physical board locations, such as mapping the clock pin to H16 on the ping Z2, like that. We have to assign all these clock pin, button pin, and reset pin to H16, D19, and D20 respectively. And after that, instead of the graphical interface, we can assign these LED pins using TCL commands for 8-bit output bus called LED pins. And once all pins are mapped, we migrate the pin planning project into an RTL project. So here, this is where we will be assigning output pins to LED pin 0 to LED pin 7. And then after setting up this, then you have to provide the pin location to all of the LED pins here by just entering all these commands in the TCL console. Then you have to save the constraint file and write the file name as UART_LED_ping. Then you have to migrate to RTL project. Then what you have to do is you have to add all the source files. Then you have to copy this file ps_init.tcl in your project directory, which is lab5, and then you have to run this command in the TCL console, and then it will create a top level wrapper file called system_wrapper.v, which will instantiate the system.bd, the block design. Then you can just double click on the UART_LED for the ping Z2 entry to view its content. And we can check that the baud rate and clock rate should be 115200 and 125 megahertz respectively. So I can show you here, like it is my UART_top. If I go in this file, UART_LED, if I go in this file, then the baud rate is this and the clock rate is 125 megahertz, which is set up correctly. Then the next step is that we move on to synthesis and timing. So we can run the synthesis by just clicking this run synthesis here. To save time, I have already done that, and I can show you the schematic that is generated after running the synthesis, and it is like this. Then the next step would be to run the implementation, and the schematic that I get from here is like this. Then we have to do some analyzing some timing constraints. Like from there, we launch the constraints wizard, and the wizard helps us specify our clock frequency. So if you follow the all the instructions given here, then you have to set up the clock frequency. Like here for the ping Z2, you have to set it up as 125 megahertz, and you have to proceed in this way. You can follow all these steps by reading this documentation. So the main thing is, after running the analysis, what you see here is that the design timing summary report provides a brief first setup and holds slack information. So you can see that there are two timing failures under the hold check that you can see from here. So we can go here and try to make failing paths to zero. So for that, what we have to do is, so this is basically the schematic of the path which is getting failed, and so to make the failing endpoints to zero, we have to double click on the first failing path from the top and see the detailed analysis that you can see after click on this, and the output path delay can be reduced by placing the register in IOP, which you can do by pasting this command in the TCL console, these two commands. Then you have to save this constraint file, and then you will get something like this. I have already done this. So if I go in design timing summary, then you can see that total negative select TNS is now 0 nanosecond, and there are no failing endpoints. You can see here it is coming as 0. So now our next crucial step would be to generate the bit stream to verify our output and to verify the hardware. So we generate the bit stream by clicking on this generate bit stream, and as I have already done this, so I will move forward by just clicking the open target. So first of all, I have to connect my ping Z2 board with my laptop using the micro USB cable, and then I will just press open target and then auto connect. And you can see here in the hardware manager, it is showing the server like localhost, this thing. It means that my ping Z2 board is connected, but I have to program the device by pressing on this program device and then OK program. And you can see this my board is now programmed. One crucial step for the ping Z2 board, because our design uses the Zinc processing system to route the UART data to our FPGA logic. We need to initialize the ARM processor and load our software application. So I will just go to the interpreter. And you have to change your current directory to this location where your Xilinx application is downloaded. Then you have to just run these all these commands in sequence one by one. We will select target one. The path for this file ps7 underscore net init.tcl can be defined in your case. So just change it and run this command here. Now we will switch to target 2 and run this command. The path for this file uh, will also be different for your case. You can see successfully downloaded, and now just write CUI. You can see the ARM Cortex C9 MP core has 0 target 2 running. The processor is running now. Now we have to just move to our Vivado project, and you have to open Terra tab, select serial, and then USB serial port, which is COM7 in my case, then OK. In the setup, then serial port speed should be 115200, and then in terminal just check this local echo box. So each character has an ASCII value, and this value is represented in 8-bit binary. The design maps in this binary value to LEDs. So for example, if I type the letter A, its ASCII value is 65. So which in binary is 0100 0001. Each bit corresponds to an LED. So that means here 1 means that LED will be turned on, and 0 means that LED will be off. So ideally all 8 LEDs would show this pattern. But the pin Z2 board has only 4 onboard LEDs. So lower 4 bits are connected to the onboard LEDs, and the upper 4 bits are sent to PMOD pins, which are not visible unless external LEDs are used. So we only see 0001 in case of character capital A. So let me show you. If I if I type character capital A in the putty software, then you can see only the LED 0 is turned on, which shows that the lower 4 bits of the LEDs are 0001. And this button, which is this push button, which is button 0, if I press this, then what this do is it will swap the nibbles. Like this is now lower nibble, so if I press this, then it will be exchanged with the upper nibble. So like if I click here, you can see it is 0101. So the complete binary representation of letter capital A becomes 0100 and 0001. So similarly, I can try with the character B. If I type B, then you can see LED 0 becomes 0 and LED 1 is turned on, which is simply means that 0100 and 0010. So in similar way, you can try with all other characters, and if you see it basically behaves like a counter. Now I press D and then E and then F and then G. You can see it is a basic counter. So this design also includes an interactive feature using a push button that I have already demonstrated you. That when I press the hold button, then it will swap the lower nibble with the upper nibble. So in summary, UART input sends ASCII characters, LEDs display the binary equivalent, and only lower 4 bits are visible. And if we have to see the upper 4 bits of the binary representation, then we can use the push button to get the upper nibble of those binary representation. So this experiment demonstrates how digital system processes manipulate and display data in real time using FPGA hardware. So I hope you understand the complete process. Thank you.